2, 3. So taking is equal to I 1, 2, 3, we got actually 6 terms. Look, there is a F21 corresponding to 1, 2. But F12 is minus of F21. So when we combine these two, I get 0. Similarly, F31, F13. When I combine these two, 0. F23, F32, 0. So sum of this term actually vanishes. This term is 0. Okay?
Yes, sir.
Okay. So now I have only this sum of external force. If I can only write is its total external force. Total external force. Okay. Now look this term, MI dot. Okay. Oh, sorry, I take it derivatives, double derivatives only here MI. This question, second derivative, MI. Look here. Okay. Actually, it is dp by dt, dp by dt, p is mv, and v is dr by dt. We have dp by dt, p is mv. So I can write this as d by dt of mv, but v is equal to dr by dt. So I write d square r by dt square MI. Okay? Now but look, MI, summed over I, MI. We have a term which is called center of mass. Where whole mass of the body is concentrated, whose position vector is, we have a formula R is equal to summed over I, MI by summed over MI. Isn't it? The position vector of center of mass. Summed over MI is nothing but whole mass of the system, capital M. So in place of the summed over MI, I can write capital M into R, where M is the mass of system and R is the radius vector of the center of mass. Okay? Hello?
Yes, sir.
Yes, sir.
So repeating this two, I can write this. M d square r by dt square is equal to total external force. So if the external force vanishes, this term is a conserved quantity, means, okay, m dr by dt or mv is a conserved quantity which is a linear momentum. So this is a conservation statement that the linear momentum of a system of particle, if the total external force is 0, total linear momentum is a conserved quantity. And because this quantity is a linear momentum, P is equal to mv dr by dt. Similarly, correspondingly, we can found the angular momentum because we already discussed for a single particle. We extend it only to system of particle. For a system of particles, I have already discussed that the total torque for a single particle R cross P, for ith particle Ri. Okay. Now torque R cross F. We know total torque is equal to summed of torque acting on individual particle tau I. But tau is equal to R cross F. Summed over Ri cross Fi. But F is equal to Pi dot. So I can write total torque is equal to summed over Ri Pi dot. Okay. Again, using this, I already saw that this is nothing but derivative of R cross Pi, because second term will be 0, and d by dt of A cross B, A dot A cross dv by dt plus dA by dt cross B. On that term will be 0, so it will be this, which is your torque. Torque means rate of change of angular momentum L. So this is your L. But R cross Pi, one side we got this, but from this term I also write Ri cross Fi. But Fi is equal to Fie plus Fij. Here I can write this term summed over Ri. Okay, change the color. This equal to summed over Ri cross Fi means external force plus internal force. Fie plus Fij or Fji summed over J. Okay, which is written here. So Ri cross Fi plus Ri cross Fji. But we know Fji is equal to minus of Fij. If we take the sum, Fji plus Rj because the sum over both I and j. If you repeat I, this pair like term comes Ri cross Fji plus Rj cross Fij, which I write Fij as minus of Fji. I found Ri minus Rj cross Fji. But Ri Fij according to Newton's third law, force acts along the line joining them. Fji acts along the line joining them means Ri Rj, and Ri minus Rj is also acts along same line. So that means direction of both are same. Angle between them is 0. Since a cross product, angle between them 0 means this is vanishes. So this term actually vanishes. Only this first term of RHS remains as it. R cross F is equal to torque. So we found R cross Fij is equal to torque. dl by dt is equal to Ne. Similarly, what we do for a single particle, here we can do for a system of particle. So it indicates that the L is constant time if the applied torque is 0. The conservation of angular momentum. Similarly, we can get the conservation of energy. Actually, another term here you can show how the angular momentum of a system related to its angular momentum of its center of mass. Okay, let's say this is your center of mass position. This is our, it is our ith particle. Position vector of ith particle is Ri. Position vector of center of mass is capital R, and let's say Ri prime is the position vector of the ith particle with respect to center of mass. From this figure, you can say using triangle law, Ri Ri is equal to how much? Vector R plus Ri prime. Is not it? Hello?
Yes, sir.
Yes, sir.
R, all are vectors. Ri is equal to R plus Ri prime. Okay. So if you take a derivative, Vi is equal to, let's say V, or V plus Vi prime. V means this V means dr by dt. Okay. If the velocity is like this. So now calculate the momentum. Momentum is equal to what? Momentum is equal to MVI. So mi V prime. So momentum is how much? I write like this. Momentum. Okay. Angular momentum is equal to Ri cross Pi. In place of Ri, put Ri prime plus R. In place of Pi is equal Mi Vi. In place of Vi, put this. So we have actually 4 terms. Actually, it will be summed over I. In place of Ri, we write Ri prime plus capital R. All are vectors. cross pi. Pi means we have to mi vi. Mi in place of vi I write vi prime plus v. Now if I simplify, we have four terms: ri prime cross mi take outside mi, ri prime cross vi prime plus ri prime cross v, r cross vi prime plus r cross v. Okay, we have four terms. Written here four terms: mi r cross v, ri prime plus vi prime, ri prime plus v. Okay, r cross my ri prime. Okay, look here. Okay, so vi prime you can write it as d ri prime by dt. If more simplify, it is d ri prime by dt, and this is d capital R by dt. Okay, so I substitute, I have four terms like this. Okay, but where is sum of I mi ri prime? Actually, this is 0 because mi ri prime is equal to, by definition, how much? Summed over I mi ri prime. Ri prime is equal to ri minus r. So it is basically summed over mi ri minus r. That is summed over I mi ri minus summed over I mi capital R. For this term, by definition of center of mass, nothing but m into r. And summed over mi is nothing but capital M into r. Mr minus mr is equal to how much? 0. So this term actually 0. If you using vector algebra from this figure, you can show that this is not but 0. So when those mi ri prime where, that actually vanishes 0. So finally we have only two terms, this one and this one, r cross mv. So summed over I take here, and ri prime plus pi prime, mi prime pi prime. So angular momentum of a system is equal to angular momentum of its center of mass plus angular momentum with respect to center of mass. Same thing for kinetic energy. Kinetic energy of a system is equal to kinetic energy of its center of mass plus kinetic energy with respect to its center of mass. Okay? Hello?
Yes, sir.
Okay.
Yes, sir.
Then so energy conservation, what we have to do for a single particle, you can only extend it. That idea that W12 is equal to change in kinetic energy, you know that work done is equal to change in kinetic energy, and if it is a conservative system, you can put it is equal to change in potential energy. Finally, you get energy is a conserved quantity. Okay, I'm not going to details. Very similar one. We go to one topic, and this is all about part one. Part two or unit two topic is constant. Okay. Now constant side is visible.
Yes, sir.
Okay.
Yes,
Come to
sir.
this
Yes, sir.
very important one. Constants and generalized coordinate. Constants. Literally, constants mean limitation or restrictions. Constants limit the motion of the system. Constant limit the motion of the system. For a system, the number of coordinates which can vary independently is called the number of degrees of freedom of the system. Number of degrees of freedom of system means the number of coordinates which can vary independently. Or you can say the number of coordinates required to completely specify the dynamics of the system or the configuration of the system. The degree of freedom means number of independent coordinates required to completely specify the configuration of the system. Or in other word, one you can say the number of coordinate we can vary independently. Suppose a motion in space, we have three coordinate: x coordinate, y coordinate, z coordinate. They can vary independently. So degree of freedom is 3. Due to constraints, degree of freedom of a system decreases. So due to constant, degree of freedom of system decreases. Suppose for a bird can move in this side of fly or move this side x, y, z. But for us, we can move only either x or y. We cannot fly. So we have 2 degree of freedom, where a bird has 3 degree of freedom. So we have a constant that we cannot fly. The human being a degree of freedom is 2, so it cannot fly. It cannot change its jet direction, you can say. But a bird can fly, bird can move any direction. It can change its position along space, so it has 3 degree of freedom. So we have a constraint. Constant reduces the degree of freedom. Similarly, for motion of a pendulum, if
Sir,
a
I have a doubt.
ah
If we go through any ladder, matlab CD,
ah
then how many variations will have and what will be our constraint?
so to constant, let's say that ladder is on the floor. Okay, you have only changed its 2 positions. If ladder is straight, your degree of freedom is 1. Only one height you can say change. But if ladder
Yes,
is
sir.
in tilted, slightly tilted, then you have 2 coordinates you have to know. You are just like in a plane. Ladder is behaves as a plane. So we need 2 coordinates. Your degree of freedom is M2, not 3. 2. If ladder is straight, just like a ant is moving on a thread, it has only 1 degree of freedom. Okay, this straight line. If it is bent, then we have 2 degree of freedom. It behaves like a plane. But 2 coordinates are changing. But it is straight, only 1 coordinate is changing. Okay. If it is tilted, then your 2 coordinate is changing. The degree of freedom is 2. Okay.
Okay, sir. Okay, sir. Thank you.
Uh, for a simple pendulum, so let's say suppose a bob can move. It has 3 degree of freedom. But when you attach it a string and with a rigid support, then it is degree of freedom only 1, which is given by this angle theta. So okay. Similarly, bead sliding on a rotating wire. Okay, its degree of freedom reduces. Now, constants may be classified in various ways. Holonomic constants. If the condition of constraint can be expressed as equations connecting the coordinates of the particles having the form function of r1, r2, r3 or coordinate and time is 0. Time is optional, is 0. Then we call it a holonomic constant. Two things is important. Holonomic constant case, we have to express the constraint equation with a equality symbol. Second thing is constant equation only contain position coordinates and time. Okay. If constant is only position coordinates and time, then we call it a holonomic constant. For example, a simple pendulum. A simple pendulum constant is the length of this rod or string is fixed L, which is actually if you treat a polar coordinate, that is R. So R mod of R is fixed L, or we can say R minus L is equal to 0. Is the equation of constant, the equality symbol and only position. A rigid body constant. Rigid body means the distance between any 2 points is fixed. In a rigid body, the distance between any 2 points is constant. So distance between any 2 points is, let's say one is Ri position vector, another Rj. Ri minus Rj square is equal to Cij square. So Ri minus Rj square minus Cij square is equal to 0. This is another example of holonomic constant. Two things: equality sign and it contains only coordinates and time. Then third is the particle constant to move along any curve or a given surface. The particle is constant in the position. Okay. Suppose a particle moving on a sphere, a radius r, then it always is r fixed. Non-holonomic constant. If the condition of constant cannot be expressed in the form of equation 1. Either there is a inequality sign or there is a content velocity. Then we call a non-holonomic constant. For non-holonomic constant, the condition of constant may contain velocity terms or inequalities. Clear? Hello?
Yes, sir.
For
Yes, sir.
example, the motion of a particle placed on the surface of a sphere in a gravitational field. Okay. Suppose the motion of a stone. If it when it moves, when it comes here, due to gravity, it falls down. So here, position vector is greater than r. Okay. So condition is r square greater than equal to a square. Inequality symbol, r square minus a square greater than equal to 0. But if it is ant is moving on the surface of a sphere, then ant cannot fall down. It will be moved on this. So it is a holonomic system. But if it is stone or generally written in the gravitational field. Gravitational field means when it come here, it will fall down due to gravity. Second is the motion of gas molecules in a container. Molecules are moving randomly, but they cannot go through across this boundary. So most here constant is r less than equal to a, the radius of this field. That is less than equal to inequality symbol. So it is a non-holonomic constant. Sometimes the constants are specified by restriction on the velocities rather than on coordinates. And still the constant are holonomic. The fact is that velocity equation is integrable to yield the equation of time. Sometimes in direct equation there is velocity term, but integrating that we can get equation like this. We call it holonomic constant. Okay. Just like motion of cylinder rolling motion, rolling of a cylinder in a plane, inclined plane. That type of motion. Okay. Again, depending on the time, if the condition of constant don't depend on time, then the constant are called scleronomos. A simple pendulum, rigid body, there is no time here. In equation of motion, there is no time here. So they are scleronomos constant. Rheonomos constant means if the equation of constant content the time as explicit variable, then the constant are said to be rheonomos. Beads sliding on a moving wire, pendulum with variable length. Suppose pendulum with variable length. The length varies with time. Bead sliding on a wire with time. There is a bead moving on a rotating wire. You are rotating it at a particular time. It may be move outside this wire. And an expanding or contracting spherical container of gas. Suppose the size is actually increasing or decreasing. Size of the container or increase varying. Then we call it a time dependent constant or rheonomic constant. Okay? Hello?
Okay, sir.
Hmm.
Okay, sir.
Actually, due to introduction of constraint, we face two problems. First problem is the coordinates are all no more independent. Okay, these coordinates are connected by suppose your Ri and Rj are connected by this equation. If I know Ri, I can calculate Rj using this equation. Ri square is equal to Cij square plus Rj square. So all the coordinates are no more independent. By independent means suppose I have equation force is equal to Pi dot or F is equal to P or summed over total force Pi is equal to summed over Pi dot. Pi comes means mi d square r by dt square. If your all coordinates are independent, then this is true for all I. This is true for 1, true for 2, true for 3. If all are independent, then I say f1 is equal to p1 dot, f2 p2 dot, f3 p3 dot. Okay. So that means what? f5 pi dot is equal to 0 minus pi dot 0. So f1 minus p1 dot is equal to 0. f2 minus p2 dot 0. But if they are not independent, suppose there relation exists between f1 and f2. So I cannot say f1 minus p1 dot 0 because f1 plus f2 0 or p1 plus p2 0 independently they may separately 0. Okay. So if they are not independent, we cannot say f1 minus p1 dot 0. If they are independent, then it is true for all I. True for 1, for 2, because they are 1, 2 are independent. They have no relation. Clear? So one thing is, due to constraint, the coordinates are no more all independent. Second thing is force of constraint. The force of constraint is unknown throughout the problem. We don't know what the force is acting due to constraint. Okay. Constraint introduce two type of difficulties in the solution of mechanical problem. First, the coordinates are no longer all independent since they are connected by equation of constraint, and the equation of motion are not all independent. Second, the forces of constraint are unknown throughout the problem. In other words, imposing constraint on the system is simply another method of stating that there are forces present in the problem that cannot be specified directly but are known rather in terms of their effect on the motion of the system. Because someone is constant in that, we don't know that force. Someone is responsible for that don't allow that molecules to go beyond that gas container. Someone is restricting them, but we don't know that force. Okay. In the case of holonomic constraint, the first problem means no coordinates are no longer independent. We can make it independent by using the term generalized coordinate, using set of independent coordinate for holonomic constraint only. The first difficulty, this one, is solved by the generalized coordinate, and the second difficulty can be solved by one procedure known as D'Alembert's principle. Okay. So the constraint creates two problems. First problem that all coordinates are no more independent. Second is the force of constraint is unknown throughout the problem. And first problem for holonomic system can be solved by the introduction of generalized coordinate. And second problem can be solved by D'Alembert's principle. Okay. Go to first coordinate, generalized coordinate. What is actually generalized coordinate? A system of n particles free from constraint, we have 3n independent coordinates of degree of freedom. For one particle, we have 3 coordinates. If 2 particles, 6. N particles, 3n coordinates. If there is no constraint. If k constraints exist, then we have 3n minus k number of independent coordinates. Constraint decreases the degree of freedom, independent coordinates. Okay. This elimination of the dependent coordinates can be done by introducing a new set of 3n minus k independent variables. So for if there are k constant, we need 3n minus k number of coordinates. How we get 3n minus k from 3n? It is quite difficult. But there is another process. If we can set a new 3n minus k number of coordinates, then we call it generalized coordinates. We can use it for solving our problem. So generalized coordinates are a set of independent coordinates. Okay, used to describe the complete motion of the system. Set of independent, they're not dependent. Okay, independent coordinates. So elimination of the dependent coordinates can be done into a new set of independent coordinates. Generally, symbol is q1, q2, q3, and k minus k, and they are we can count our old coordinate from using the generalized coordinates, and reversely q1 is a function of r1 to rn and t. These are the connecting equations. R1 to Rn can be expressed as a Q1 to this, and reversely Q1 can express as a function of R1 to Rn, Q3n minus k as a function of R1 to Rn. Clear? Hello?
Yes, sir.
Okay. And another property, this transformation equation from set Ri to Qi set, we can also transform back to get Qi from Ri. What are the properties of generalized coordinate? Generalized coordinates are the set of independent coordinates which are required to completely specify the configuration of any system without constraint, or in case of constant motion, configuration of those systems which are bounded by holonomic constraint. Generalized coordinates can be used for any system which are no constraint. Suppose for motion of the planet around the sun. Here we don't use the XYZ coordinate. We use polar coordinates, R theta coordinate. Here there is no constant. Okay. But if we constant, then it will be holonomic constant. So generalized coordinate used set of independent coordinate used to specify the configuration of any system without constant or system with holonomic constant. So its general symbol is Q, small q, coordinate J, where J varies from 1 to F. F means number of degree of freedom. If there are K constant, degree of freedom 3 n minus K. Second important thing is usually generalized coordinate Qj, unlike the Cartesian coordinate, will not divide into convenient group of 3. In Cartesian coordinate, we know that if 3 coordinate x, y, z, what means that its position vector will be xi cap plus yj cap plus zk cap. It can be divided in group of 3. So two particles x1, y1, z1, x2, y2, z2. Three particles x3, y3, z3. But here generalized coordinate cannot be divided like that group of 3. Okay, Cartesian coordinate can be used as generalized coordinate term used as an alternative to Cartesian coordinate. Okay, so in general cannot be divided in a group of 3. Generalized coordinate may be a position coordinate. In Cartesian coordinate means you understand a position coordinate, x position, y position. But generalized coordinates are not always position coordinate. It may be an angle, some quantitative dimension of energy, angular momentum. Like simple pendulum, coordinate is theta angle. It can be any quantity. In case of simple pendulum, generalized coordinate angle. In the problem of particle moving central force field, there is no constant, but we use polar coordinates. What I have told already. So this is our general coordinate. In general, generalized coordinate means coordinate different from Cartesian coordinate. But sometimes Cartesian coordinates are also comes under generalized coordinate. It is generalized. But it term used to as it different from Cartesian. Okay? These are the property of generalized coordinate. Hello?
Yes, sir.
Yes, sir.
Okay. Then we go to the second part, D'Alembert's principle. 1 minute. Which is the final. Okay. So you have already this. The second problem, the force of constants are no more. Sorry, force of constant is unknown throughout the problem. The first problem can be solved by general. The second problem. Okay. First, for solving the second problem, also there is one line. If the constant is non-holonomic, then for solving first problem, instead of generalized coordinate, we can solve those problem, some problem, not all, some problem by using Lagrange's method of Lagrange's multiplier. Okay. Okay. For the second problem, uh, we need to formulate the mechanics in such a way that the force of constant will disappear and then we will deal only with the known applied force. So for remove force of constant are unknown. So to solve this problem, we use some kind of mechanics such that the force of constant can be completely disappear from our problem. So that we deal with only applied force. Okay. Suppose, for example, a hint of this procedure can be taken from the motion of a rigid body. And I have already told, a rigid body means inside a rigid body, the distance between any 2 points is fixed. So the equation of constant equation is this. But from Newton's laws of action and reaction, we know that the force acting on ith particle is due to Fij, it acts along the line joining them, Rij. So here internal force Fij are the force of constant and Rij distance between 2 points fixed. So what is Drij? For a rigid body, since distance between 2 points is fixed, Drij is perpendicular Rij. And Dij vanishes. So force into displacement vanishes. Work done is 0. Okay. For a rigid body, Rij is fixed. So Drij basically 0. Fij or Drij is 0. Or Fij is perpendicular to Rij. But for a rigid body, the work done by the force of constant 0. Now, D'Alembert want to use this principle for all systems. For this, you develop a mechanism or procedure. D'Alembert followed up this clue and developed a mechanism to generalize the idea contained in. Okay. We go to details too. Before that, we have to discuss a few terms. We have already discussed generalized coordinate. Another term is generalized velocity, derivative of generalized coordinate, dqj by dt. Similarly, generalized momentum, mi qj dot. Another term is virtual displacement. A virtual displacement of a system refers to a change in the configuration of the system as a result of arbitrary infinitesimal change of the coordinates consistent with the forces and constant imposed on the system. Actually, actual displacement means system moves with time or if the system changes. Virtual displacement means due to force of constant, there is a some kind of change in the of the particle inside that system. That is virtual, not actual displacement. It does not change its position, system does not change its position with time. But inside the system, the particle may change their position due to force of constant. That is virtual displacement, with symbol delta arises. At a particular instant of time, it occurs at a particular instant of time. Here time, actual displacement time is the variable. With time, its system changes. But at a particular instant of time, whatever change occurs due to the internal force of constant is called virtual displacement. Okay. In a particular instant of time, the time doesn't vary. The displacement called virtual displacement is to actual displacement system which occur in time dt. For a system, we learned that coordinate can be a function of generalized coordinate q1 to q3 n minus k t. So delta ri is the small variation can be written as del ri by del q1, delta q1, del ri by del q2, delta q2, up to del ri by del t by delta t of but here at a particular instant of time, so del t is 0, so this term vanishes. Only this term, or in term of sum, I can write j varies from 1 to 3 n minus k del ri by del qj into delta qj. Is not it? Virtual displacement लिखे हो ना नहीं?
Yes,
Hello?
yes, sir.
Yes, sir.
Okay.
Yes, sir.
Then virtual work. The work done due to virtual displacement is called virtual work. An element of work done by force due to virtual displacement is called virtual work. Fi dot delta ri, virtual displacement. The work done on ith particle. But this force on ith particle, we will know external force plus internal force. Or here you can say internal force as force of constant. Applied force plus force of constant. So applied force plus force of constant. So now there are two terms, Fia dot delta ri or Fic plus delta ri. But constant are said to be workless constant if the virtual work done by force of constant is 0. Sometimes you assume that virtual work done by force of constant is 0, then we call it a workless constant. So then only we have one term, Fia dot delta ri is equal to 0. The concept of workless constant is not only valid for rigid body, but also for a large number of systems. Okay. Then principle of virtual work. According to principle of virtual work, the condition for equilibrium, actually when total force acting on the system is 0, we call a system is in equilibrium. When total force acting on the system is 0 or vanishes, we call it in equilibrium. If total so according to principle of virtual work, the condition for equilibrium of system with workless constant is that the virtual work of the applied force vanishes. Now, principle of virtual work means the work done by virtual displacement is 0. How you prove it? You know at equilibrium F is equal to 0. But F, so summed over Fi is 0, Fi is 0. Fi has two part, Fia plus Fic. So Fia dot delta ri 0, Fic dot delta ri 0. If it is workless constant, then Fic dot delta ri 0. So only we have Fia dot delta ri 0, which is called principle of virtual work. But here, system is in equilibrium, rest. D'Alembert try to apply it for a dynamic system. For an equilibrium system, F is equal to 0. But for a dynamic system, moving system, F is equal to how much? Hello? According to Newton's second law, F is equal to
dp by dt.
dp by dt or pi dot. So I can make it 0 by writing F minus pi dot is equal to 0. F minus pi dot 0. So now right hand side is same 0. Okay. D. Alamo tried that. He tried to make a dynamic system to static system. So the coefficient of delta Ri in the equation no longer be set to 0. But delta Ri not. Second problem is here sum by Fia dot delta Ri is equal to 0. But all Ri are not independent. They are connected through equation of constant. So next time we have to convert the del Ri to del Qj. What we have already discussed, del Ri can be written as in terms of del Qj. Like this. The coefficient of all del Qj are 0. Because del Qj are independent component. Okay. D alone apply these two things. In order to put the coefficient to 0, we transform all delta Ri to delta Qj. Second thing, for a dynamic system, D Alembert use okay, Newton's second law. Okay. D. Alembert developed a mechanism for removing force of constant from the problem related to general motion of the system. According to Newton's second law, Fi is equal to Pi dot, Fi minus Pi dot is equal to 0. Okay. So, which implies that a system will be in equilibrium under a force equal to the actual force plus a reverse effective force. It's minus Pi dot reverse effective force. In this way, dynamic reduces static. Or the static, now it behaves like a static. Right hand side is 0, force 0 means equilibrium. Okay. So now Fi dot delta Ri is 0. In place of Fi, I can write Fi minus Pi dot delta Ri is equal to 0. Now I can put Fi is equal to Fia plus Fi3. Now we have three terms. If it is workless constant, then Fic dot delta Ri is 0. Only I have two terms, Fia minus Pi dot delta Ri. This equation is known as actually or represent D. Alembert's principle. Okay?
Yes, sir.
Hello?
Yes, sir.
That's simple thing, huh? D. Alembert. But it is very, very important because from this principle we can derive Lagrange's equation of motion. Okay. We have achieved our aim in that equation 5. The force of constant no longer appear. There is no force of constant. So now we can remove this superscript A. We got this equation as the D. Alembert principle means this equation. Sum over I is equal to 1 to n Fi minus Pi dot delta I is equal to 0. But it is not still in a useful form because we have delta Ri here. We have to convert the delta Ri to delta Qj and separately equate all coefficient to 0, which is basically our Lagrange's equation of motion. Next is Lagrange's equation of motion. Okay. We have already learned that. From D. Alembert's principle, we know that for a system with workless constant, the virtual work done by the system can be expressed as this term. Okay, Phi dot del Ri minus Pi dot del Ri is equal to 0. Since due to presence of constant Ri are no more all independent, we have to transform into Qj. We know this relation. Ri is a function of all Q's and T, so delta Ri is equal to del Ri by del Qj, or finally delta Ri is equal to del Ri by del Qj and delta Kj. J varies from 1 to F or 3n minus K. Okay. Now put this. We have Fi dot del Ri. Fi in place of del Ri, I use this sum over del Ri by del Qj into delta Qj. Now I take all summation over I. Where is I? I is Fi del Ri by del Qj. I Fi dot del Ri by del Qj into delta Qj. This term is nothing but generalized force. Summed over I Fi dot del Ri by del Qj is called generalized force Qj. Qj is the component of generalized force. So generalized force Qj is equal to sum over I Fi dot del Ri by del Qj. We already know that small q's need not have dimension of length because they are not coordinate always, maybe angle or anything else. Similarly, capital Qj don't necessarily have the dimension of force. The generalized force by dimension, not necessarily force. But the product of Qj and del Qj, force and displacement must be always have work. So dimension of Qj, delta Qj always work. Okay. So product of Qj and delta Qj has always a dimension of work. Okay. So here we got Qj delta Qj. Again second term, we have to simplify second term. Pi dot del Ri. Pi dot means Vi is mi Ri dot. Again its derivative. So mi Ri double dot means d square Ri by dt square. Dot delta Ri. Now take all summed over j where but del Ri is equal to this. Taking all terms containing I in the bracket, we got this sum of I is equal to 1 and mi Ri double dot del Ri by del Qj. Now simplify this term. Mi Ri double dot del Ri by del Qj. Mi d Ri dot by dt dot del Ri by del Qj. That means it is d by dt of mi is a constant derivative inside it. Mi Ri dot del Ri by del Qj d by dt of A dot B dA by dt dot B plus A dot dB by dt. We already discussed that. Now here one term derivative of this term dot del Ri by del Qj. Now I take derivative of whole term mi Ri dot del Ri by del Qj minus mi Ri dot derivative of only del Ri by del Qj. Clear?
Yes,
Hello?
sir. Yes, sir.
This is actually AB and AB. So in the term ego equation, we can interchange the differentiation with respect to T and Qj. Since T, Qj are independent variable, I can change the order of T and Qj. Okay. The d by dt del Ri by del Qj I can write as del by del Qj del Ri by dt means del Ri dot del by del Qj of Ri dot d Ri by dt Ri dot. I change the position q and x y independent means del by del x del f by del y same as del by del y del f by del x. You know that T and Qj are independent component. So now my final equation becomes Pi dot del Ri is equal to d by dt of this term mi Ri dot del Ri by del Qj minus mi Ri dot del Ri dot by del Qj into delta Qj. Okay, this is important equation. But we know that kinetic energy of a system is equal to half mv square. For ith particle, half mi Ri dot square. Vi is equal to Ri dot square. So total kinetic energy is equal to summed over I Pi. Pi is the kinetic energy ith particle. Half mi Ri dot square. Ri dot means V. Okay. But Ri dot means again Ri dot and V dot V or Ri dot Ri dot. So del T by del Qj can be written as del using chain rule del T by del Ri dot del Ri dot by del Qj. T is this much. Now take a derivative with respect to Qj. Since it is function of Ri dot, we use chain rule. Del T by del Ri dot del Ri dot by del Qj. Del T by del Ri dot is equal to 2 mi Ri dot, 2 cancel Ri dot. The second term remains same del Ri dot by del Qj. 2 have cancelled, it is mi Ri dot del Ri dot by del Qj. Again del T by del Qj dot. Again same rule del T by del Ri dot del Ri dot by del Qj dot. So del T by del Ri dot same thing. 2 cancel mi Ri dot del Ri dot by del Qj. Mi Ri dot del Ri dot by del Qj dot. But del Ri dot means del of Ri dot is d Ri by dt. Here d Qj by dt. So you may cancel dt dt. So it is only del Ri by del Qj. Also using this formula we can show that Ri is a function of this. So del Ri by dt is equal to sum over del Ri by del Qj into dQj by dt plus del Ri by dt into dt by dt. It will want only del Ri by del t. So Ri dot by Qj dot is how much? Del Ri by del Qj. So dot will be cancellation of dot. Del Ri dot by del Qj dot. This is same as del Ri by del Qj. This is same as del Ri by del Qj. So I write that del Ri by del Qj. Because we have two equations. See, first term of the equation mi dot del Ri by del Qj. Same mi dot del Ri dot cancel del Ri by del Qj. So it is basically del T by del Qj dot. Okay, go to here. Again here mi dot del Ri dot by del Qj. This one, which is nothing but del T by del Qj. So final equation I got pi del I dot is equal to d by dt of del T by del Qj dot minus del T by del Qj into delta Qj. Again using but this left hand side in A2 we have a expression. This is equal to Qj dot delta Qj. So Qj delta Qj is equal to this, or Qj minus this whole into delta Qj is equal to 0. Okay?
Yes, sir.
So you can full derivation are given here. So from this, since delta Qj are independent coordinates, so all the bracketed term must be vanishes for each j. For j is equal to 1 it is true, j is equal to 2 it is true. So we have a f number of equations for 1, 2, 3. We have f number of equations that d by dt del t by del Qj dot minus del t by del Qj is equal to capital Qj. This generalized form of Lagrange's equation. A general form of Lagrange's equation, and there are f number or 3n minus k number of equations. For j1 is true, j2 true. So here j varies from 1 to f, or 1, 2, 3 up to f or 3n minus k. Okay. This is the general form of Lagrange's equation. Clear?
Yes, sir.
Then special
Yes, sir. Yes.
exact Lagrange's equation actually for a conservative system. If we take conservative system, when the system is conservative, we know for a conservative system, forces can be derived by potential and F is negative gradient of potential. Fi is equal to minus del I by V. So if I put, then Qj changes because Qj have a form Fi dot del I by del Qj. If I put minus del IV, then to minus del IV del Ri by del Qj, but del IV is nothing, del V by del Ri, I have already tell you. So using chain rule, reverse chain rule, you can say del V by del Qj. So I think nothing but minus del V by del Qj. So here you can write for a conservative system minus del V by del Qj. So now take all to one side. So del V by del Qj come here. A minus, it will become plus. So if I take minus common, so it will be t minus V. Again, V is a function with conservative system. V is a function of position coordinate only. So del V by del Qj dot is equal to 0. Del V by del Qj dot is equal to 0. So I add 0 here. That means del V by del Qj dot 0 means del V by del Qj dot or minus del V by del. So I can write like this. That T minus B is L. Okay. So my equation becomes this. T minus 0. Now I add a 0. Because del V by del Qj dot is equal to 0. So I subtract a 0 means del V by del Qj dot. So I can write like this. Is not it? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Then I take this T minus B as L, Lagrangian. And my equation becomes d by dt del L by del Qj dot minus del L by del Qj is equal to 0. Okay. This equation is known as Lagrange's equation. Or sometimes Euler-Lagrange's equation. Because since we are fixing it as generalized coordinate, for any parameter, we call it Euler-Lagrange's equation. Okay. There are f number of j vary from 1 to f number of Lagrange's equation. But important thing is Lagrange's equations are not unique. For using this Lagrange equation, we can get equation of motion for the system. But for a single equation of motion, we have not a single Lagrangian. Just like for a single electric and magnetic field, we have not a single scalar and vector potential. We have a number of scalar and vector potentials. Okay, similarly, for a single equation of motion, we have not a single Lagrangian. Uh, Lagrangian, no unique choice of Lagrangian is not unique. But for a particular Lagrangian, we can adding another term, we can make a new Lagrangian. If f is a function of q and t, then we can say a new Lagrangian gives same equation of motion. L old Lagrangian plus df by dt. It gives same equation of motion. Okay? So Lagrangian is not unique. From Lagrange's equation, using this equation, we get the equation of motion of the system. But L is not unique. It may be we can get another n by using this equation, which will give you same equation of motion.
Yes,
Clear?
sir.
Yes, sir.
Simple applications.
Yes,
Okay. Simple application. First application, simple pendulum. We have to find equation of motion of simple pendulum using Lagrange's equation of motion. A simple pendulum means you will know that bob of mass m suspended from a rigid support by a massless and inextensible string of length L. Your angle theta is actually the generalized coordinate, and the constant is mod r minus L is equal to 0. This length is fixed. So what is the, here we use polar coordinate r theta, r is fixed, so only theta is the changing coordinate or generalized coordinate. Since it is a gravitational field, it is a conservative one, so energy is a conserved quantity. Now kinetic energy is equal to, in polar coordinates we know half m r dot square plus r square theta dot square, but here r is equal to L fixed, so r dot is equal to 0. In place of r you putting L, you get kinetic energy is equal to half m L square theta dot square. Here constant is holonomic, constant position, and scleronomos, time independent. Okay, now what the potential energy? Potential energy how you calculate? Actually, it is basically the amount of work done to bring its system from into equilibrium. For here, change in potential energy not absolute. We have to measure change. So bringing from position C to B, amount of work done to bringing the system from C to B. Okay. Or in which actually in gravitational field, we have a potential energy formula mgh, mass g, acceleration due to gravity, and the distance, the vertical distance h, height. So here vertical distance is AB. Coming from C to B means AB. AB is how much? Here OC is equal to L. Okay, this is equal to theta. So if you consider this triangle, so obviously this one L cos theta up to OA is L cos theta. So AB is equal to L minus L cos theta. Is not it?
Yes, sir.
Hello?
yes, sir.
L
Yes,
minus
sir.
L. So our potential energy is mg L minus L cos theta.
L.
So Lagrangian T minus B, nothing. Half m L square theta dot square minus mg L minus L cos theta. So here only one variable, theta. Theta. So we use Lagrange's equation d by dt del L by del theta dot minus q, in place of qj write theta. Qj dot theta dot del by theta is equal to 0. Calculate from this Lagrangian, calculate del L by del theta, using minus mgl sin theta. The theta is here only, plus mgl cos theta minus derivative mgl sin theta. Theta dot derivative means this term ml square theta dot. Putting in this equation, I got this. ml square theta double dot plus mgl sin theta is equal to 0. Generally, for a simple pendulum, amplitude is very small. That means theta is very small. If you put theta is very small, then sin theta approaches like theta. But theta is very small, Sin theta is basically theta. Is not it? Hello? For theta
Yes, sir.
small,
Yes,
use
sir.
cos theta 1, sin theta theta. So putting theta in place of sin theta, we get the equation ml square theta double dot plus mgl theta. Here putting theta is equal to 0, or dividing ml square with each term, theta double dot plus g by l theta is equal to 0. It is basically a equation of motion for a simple harmonic motion. Theta double dot omega square theta is equal to 0, omega square g by l, or omega is equal to g by l root over frequency. This is the equation of motion of a simple pendulum. Then second example is, it is clear? It's very important.
Yes, sir.
Simple pendulum. Okay.
Yes, sir.
Then Arthur's machine. Another example, a system of two unequal masses connected by an inextensible string passing over a frictionless and massless pulley constitute Arthur's machine. Okay. Actually, there are two masses. They are connected by a string, and the string is going over a pulley. Okay. Pulley of radius R. So total length is L, length of the string. If this one is X and R is the radius of the pulley, then obviously from this point to this point will be pi R. So this distance is L minus X minus pi R. Okay.
Yes, sir.
So actually here only one independent coordinate X, because one coordinate X. From one coordinate you can find other. It is similarly holonomic constants, scleronomic, no time. What is the potential energy? Potential on this and this. Actually potential energy 0 will be here. So it will be negative both below the 0. So we take negative m1 gx, because it equilibrium when two masses are here, it will be in equilibrium. So the equilibrium potential 0 is here. So it is less than 0, so formula is minus sign. Same formula mgh, m1 gx, here mgh, m2 g l minus x minus pi r. Only thing is minus sign because potential 0 lies here. So kinetic energy half mv square, half m1 x dot square plus half m2 this derivative. But here L constant derivative 0, pi r constant derivative 0, minus x dot. And square means minus square plus, so x dot square. So kinetic energy is same, half m1 plus m2 x dot square. Okay? Hello?
Sir, can you explain please the negative sign of M1 GX?
Here actually, step one thing is stable equilibrium. When we take minimum potential when the system is in stable equilibrium. Okay, where by disturbing it we cannot get the unbounded motion. No? Where when two masses are here, actually then they are in permanent rest or stable equilibrium. At that position, potential energy is minimum. Suppose two things. Suppose for example, we are putting a stone on a top place like this. When you slightly disturb it, it fell down. We call it potential energy maximum. But suppose we putting a stone here. If slightly disturb, it go here again come back to its original position. We call it the stable equilibrium and where potential energy minimum. Okay, potential energy.
Yes.
Similarly, here at that point the system has a minimum potential energy. One minimum in the positive sense 0. We take it let's say 0. So below this means we take negative sign. Huh?
Yes, sir.
Potential is not an absolute thing. Potential difference. Okay, understand. Generally here we take potential is 0, so below is negative. Absolute, there is no term absolute potential. No? So because it is a known problem, it is solved like this, taking 0 here. For any general problem, you can proceed anyway because it will not affect your equation of motion. So kinetic is this. So Lagrangian will be this half m1 m2 x dot square plus m1 gx plus m2 g l minus x pi r. But t minus v minus plus. Again, you here one coordinate x. Take the Lagrange equation in terms of x. Calculate del L by del X. We got here this del L by del X dot. From this L we got this. Okay. Putting this, we found this is the equation of motion. This is the equation of motion. for a Atwood's machine. Okay.
Yes, sir.
Another example is simple harmonic oscillator. Simple harmonic oscillator basically a spring mass system. A mass is attached to a spring and it executes a simple harmonic motion when you slightly disturb it. So here actually force is proportional to displacement, which is actually restoring force proportional to F minus proportional to minus X. Or you can say F is a minus Kx or K is the force constant. So potential energy is the amount of work done from bringing the system infinity to that point. F dot dx minus k dx, so it will half kx square. For a simple harmonic oscillator, potential energy is half kx square. Kinetic energy, as usual, half mh square. So Lagrangian T minus P. So here only one variable x. Take the Lagrange equation like this: derivative with respect to x, derivative with respect to x dot, and put here. We get the equation of motion. Okay. Mx dot means m is a constant, so it will be mx double dot by k. Dividing m each term, we got x double dot k by m x0. It is simple harmonic motion with frequency root over of k by m. Okay.
Yes, sir.
Next, another system is LC circuit. In LC circuit, inductor capacitor circuit, actually electrical energy is potential in nature and magnetic energy is kinetic in nature. Okay. The potential energy of the circuit actually, capacitor stores the energy for half Cv square converting into Q square by 2C. But current is equal to dq by dt. So your parameter is Q, charge. Because we can write current, the kinetic energy circuit means actually stored by inductor, you have Li square, I current is equal to dq by dt, so have Lq dot square. So Lagrangian is equal to half Lq dot square minus Q square by 2C. Taking derivative of Q and Q dot, we get this, and using Lagrange's equation, d by dt del L by del Q dot minus del L by 0, we got this d by dt Lq dot plus Q by C 0, Lq double dot plus Q by C 0, or Q double dot Q by LC is equal to 0. So this is equation of motion of LC circuit in comparison with a harmonic motion. We call frequency 1 by L0 root over. Clear? Hello?
Yes, sir. Yes, sir.
Next is the Hamiltonian quantity. Okay. Actually, for a conservative system, its total energy is T plus V is equal to a quantity which is known as Hamiltonian H. Okay. Hamiltonian H T plus V. In terms of Pj Qj dot, Pj is momentum, Qj coordinate, we can find an expression from energy conservation. If Lagrangian is this, Hamiltonian is summed over Pj Qj dot minus L. But J is number of generalized coordinates. J varies from 1 to F. It is the basic formula. Hamiltonian is equal to summed over Pj Qj dot minus L. If Lagrangian is given, we can calculate a Hamiltonian system by using this formula. Okay, but important thing is Lagrangian contains Qj Qj dot T, but Hamiltonian contains Qj Pj T. It is in phase space. Phase space coordinate are Qj Pj. So Lagrangian is in configuration space. Phase space. Hamiltonian is in phase space. Phase space coordinate are Qj Pj T. We use this formula and convert all Qj dot to Pj. Then I write the Hamiltonian. Otherwise, if you write in terms of Qj Q dot, then it will be wrong. A Hamiltonian always expressed in QPT, and from the calculated from this formula. Okay. There are a set of Hamiltonian equations. If Hamiltonian H is equal to this, ds is equal to how much? If it is a function of qj, pj, t, summed over j, del h by del qj, dqj, del h by del pj, dpj, plus del h by del t, dt. But we know h is equal to this using this formula. Calculate dh, dpj qj dot plus pj dqj dot minus l means dl. dl is del l by del qj dqj, del l by del qj dot dqj dot del l by del t dt. Clear? But both the equations are same. If both the equations are same, compare the coordinate. Here dqj multiplied with del L by del qj dot del L by del qj dot pj. Okay. Then we got for Lagrange expression. Okay, I think it was second unit thing. Okay, we go to that first. Discuss this one. Cyclic coordinate is it? If qj is a cyclic coordinate, then del L by del qj is equal to 0. The coordinate which does not appear in the Lagrangian is called a cyclic coordinate. Cyclic means del L by del qj 0. What it means? If a coordinate does not appear in the Lagrangian, then we call it a cyclic coordinate. Okay. I think we will discuss in the next class. There is a few things cyclic. Okay. Okay, we'll discuss in the next class because there are one cyclic one other things to discuss. Okay, any problem from today's class?
No, sir.
And doubt?
No, sir.
Sir, can you tell me the examination point of view important question?
Oh, no, yeah.
Hello?
I don't know the question pattern, but if it's long question, then important question is derivation of Lagrange equation from D'Alembert, and also the applications. One long
Sir,
question
from the
is derivation.
starting,
Hello?
derivation.
Derivation of Lagrange equation from D'Alembert. Also the
This is
simple
one.
pendulum and Atwood's machine. And find the equation of motion for simple pendulum Atwood's machine.
Yes, yes,
They are
next.
also important. These two are very important. Other things may be problem, maybe answer multiple choice. I don't know exact question pattern. Okay. Oh, I want to send those slides to you. How I can send? Is there any group, WhatsApp group?
Yes, sir, is there.
Okay, if you
You
have,
can say your number. I will add you on that group.
okay, my number is 9777
977
969
969
023.
023. Okay, sir, I will add you.
Okay. Okay, I will send the.
Our group name is Physics Squad.
Okay.
Can you add me actually Shivani one another
Yes, sir.
number?
Yes, you can say
6372
6372
540.
540
Sorry. 7205 7205
From the beginning, you say again.
7205.
From the beginning, are you saying?
From the beginning, I am telling 7205
7205
98
98
986 6
986
584.
584.
Shivani, can you add me?
Say it again, please.
Hello.
Those who are from BJP college, they can say the number in chat box. I will add them because it's quite problem to hear
Hi,
your
Shivani.
numbers.
Hello, hi Shivani.
Yes, sir.
Can you add me in this group?
Those are from BJP college only.
No, I am not from BJP college. That's why I am asking.
Okay. So that group
My number is
in chat box you write. Don't say me. You just write in chat box.
It is right. Those who are from BJP, they write in the chat box. C will add.
With your number, please kindly in bracket tell your study center so that I can know.
Okay, today's class is over. Actually, I will leaving.
Sir, I have already added in the group. Have you
Okay,
got the
okay.
invitation?
Okay. Invitation. Yes, yes.
Sir, did you got the invitation?
Yes, yes, I got the invitation. Yes, I joined. I'm checking the slide. Okay, I joined the group. I'm leaving. Okay, thank you.
Thank you, sir.
Thank you, sir.
Riazul Alam Khan, which study center you are? Hello.
Shivani, I have sent my number in the chat box. Can you put access, sir?
Yes. I will add it later. I will add it.
Thank you.
Shraddhanjali Khatta, which study center?
Sibel ma'am, I have shared my number, Priyabrata from MPC
Yes,
Balikata.
sir.
Have you got it?
Yes.
Yes.
In chat box I have got.
Yes, please add me in that group.
Mm-hmm.
Thank you.
With the number, kindly write your study center in the bracket.
Annie, did you add me? I have sent my
Ye-
number.
Yes, I will add you later. I am taking screenshot of all the numbers so that I can add it later.
Thank you.